This video is going to look at two important aspects of a buffer. One of them has to do with buffer capacity, and the other has to do with the pH range of a buffer, like how effectively a buffer will work within a narrow pH range. Okay, so let's start with, buffering capacity. So in terms of buffer capacity, let's say we've got some buffer. We could have, let's just do acetic acid and acetate ion. So it could be sodium acetate. So we have our buffer that we've got our weak acid, and we have our conjugate base, which is really the salt. So those two components. And we're looking at, when we talk about buffer capacity, we're talking about how much strong base can be added before that pH changes, or how much strong acid can be added before that pH is going to change. So buffer capacity, if you think about the term capacity, how much something can hold. So the buffer capacity is the amount of strong acid or strong base. So I'm just going to do H plus and OH minus to represent strong acid or strong base. The amount of that the buffer can absorb before pH changes too much. Now it's going to change a little bit, but we're talking about a larger pH change. So a buffer with a large buffer capacity is going to have lots of buffering components so that it's going to be able to take or consume lots of H plus strong acid, sorry, you can't read that, or lots of OH minus strong base. If we look at Henderson-Hasselbalch, because I think this is an easy equation to look at because you see everything in there, we're going to see that pH depends on pKa, and we need to remember that pKa is the negative log of Ka, and then the log of the concentration of the conjugate base and the concentration of the acid. So pH is going to, of the buffer, is going to depend on the Ka of the acid that's chosen. It's also going to depend on the concentrations of the conjugate the conjugate base and the acid. If we're talking about a basic buffer, then it's going to be the conjugate base and the concentration of the acid. The larger these two concentrations are, the more strong acid or strong base the buffer is going to be able to consume and still maintain that pH. Okay, so let's say we've got these two components, and let's say we've got 1 molar acetic acid and we have 1 molar acetate. A buffer like that is going to be able to consume more strong acid or strong base before the pH changes than if you had 0.1 molar solutions of each, simply because you've just got more of each of the buffering components. So the greater the amounts of this conjugate acid-base pair, the more resistant is this ratio to changes in pH, and you'll have a smaller change in pH. So that's buffer capacity. Now what we want to look at is the pH range of a buffer. So what I want to do is clean this up, and then we'll talk about that. Okay, so now we're talking about pH range. Okay, so the pH range for a buffer is that range in pH over which a buffer is effectively going to work. So, I don't know, let's say this is our pH scale 0 to 14, and we've created this. If we go back and we think about that buffer that we had before in the previous example, we've got acetic acid, and we have its salt or conjugate base, the acetate ion. This buffer is going to work most effectively around a pH of 4.74. So we're looking at kind of in this range, and how do we stay in that range? And when we're talking about buffers, they're resisting a change in either direction. So if strong acid were added, that would drive the pH lower, and so wanting to keep the pH kind of here. And if strong base were added, wanting to keep the pH close to here. Okay, so when we're looking at Henderson-Hasselbalch, we can see that when the concentration of our conjugate base and our acid are equal, pH is going to equal pKa. Okay, so let's say, let me just do an example. Let's say we've got concentrations of 0.5 and 0.5. When we divide those two numbers by each other, we get 1. The log of 1 is 0. And so when those concentrations are equal, pH is going to be equal to pKa. This relationship, where you've got pH being equal to pKa, or if you're thinking POH, if you're thinking about a basic buffer, POH being equal to pKb, this relationship gives the optimal range, optimal pH of any buffer. So when you're selecting a buffer, you want to try to pick one that has a pKa that's close to the desired pH. So let's say that I want a buffer that's a pH of 5. What I'm looking for is I'm looking for a buffer that has a pKa that's really close to 5. So this acetic acid acetate combination would be a good one for that, because the Ka for acetic acid is 1.8 times 10 to the negative 5th, and pKa is the negative log of 1.8 times 10 to the negative 5th, which is 4.74. These two are very close, so this would be a suitable buffer for a pH of 5. Now, what would be a crummy buffer? One of the things that we know is that, I'm going to write the ratio back up here again. And I'm going to get rid of our POH one, because I don't want to look at that. When one of these components is 10 times larger than the other one, so we can have a 10 to 1 ratio or a 1 to 10 ratio, there's not much buffering. That the buffering is poor. So we want this ratio to be as close to 1 as possible, and the closer it gets to a 1 to 10 ratio, the buffering action is going to decrease and more. So the best buffers have a, their range is within, let me go back to a color I haven't used. I've used that. Okay, sorry. Plus or minus 1 pH unit of pKa. So ideally we want these two to be equal to each other, but if we don't have that option, we want it to be pKa plus or minus 1. We don't want it to go beyond that. Okay, so I need to show you an example of how we would select a buffer from a list of acids. Okay, so here's our example. We need a solution that's buffered at a pH of 4.30, and we're provided with a list of acids and their Kas. And then the question also wants to know what the ratio is required for each system to yield a pH of 4.30. So this is what we're going to do. First thing you want to do is you want to calculate the pKa's of all of these. And to do that, pKa is equal to the negative log of Ka. So I want to do the negative log of all of these Ka's. And I'm going to do each in a different color so we can see them. So pKa or chloroacetic acid is the negative log of this 1.35 times 10 to the negative 6th. Nope, sorry, 10 to the negative 3rd. 2.87. And then propanoic acid, the pKa for propanoic acid, negative log of 1.3 times 10 to the negative 5th is 4.87. pKa for benzenoic acid, negative log of 6.4 times 10 to the negative 5th is 4.19. And pKa for hypochlorous acid, negative log of 3.5 times 10 to the negative 8 is 7.46. Okay, while I'm thinking about it, let's say you're given a question like this on multiple choice, and the numbers that you're given, you're not able to calculate pH because you don't have a calculator. Whatever power the 10 is raised to, your negative log of that is going to be really close to a positive value of this. So if you kind of look, this would be really close to 3, this is really close to 5, this one's kind of close to 5, this one's kind of close to 7. So that's a way to estimate. Okay, so now once we've done this, let's use Henderson-Hasselbalch. So we've got pH equals pKa plus the log of the conjugate base concentration divided by the acid concentration. All right, now I want to use what they're using here. So if I look at these two, the one that has the proton is the acid. So I'm going to change this acid and I'm going to make it Ha. And then the conjugate base is going to be the anion without the proton. So this is going to be A minus. So the thing we need to notice here is this ratio is the inverse. So we want a pH of 4.30. Now, if we look, remember we talked about in the previous slide how the ideal buffer is one where pH and pKa are really close to each other because we want this ratio to be as close to 1 as possible. So if I look at these pKa values I've calculated, I don't want chloroacetic acid, it's too far off. I don't want hypochlorous acid, it's too far off. If I look at these two, kind of close. 4.19 is much closer than 4.87, so I'm going to start with the 4.19, and I'm going to put that in as my pKa, plus the log of the conjugate base concentration divided by concentration of the acid. So combining like terms will give me 0.11 equals the log of A minus concentration divided by HA concentration. I'm going to do 10 to each of these, and when I do that I will get 1.29 is going to equal the concentration of the conjugate base divided by the concentration of the acid. But I'm really asked for the reverse, so I'm going to do the inverse of both sides, which will give me 1 divided by 1.29, which is 0.78, equals the acid concentration divided by the conjugate base concentration. And that's close to 1. Now, if you wanted to be sure, you could go back and you could substitute 4.87 in and see what you would get with that. I did that. I'm not going to redo it again for you, but I'll tell you what, when I did that and I solved, I got 3.8. Well, this ratio is much closer to 1, so benzoic acid is the buffer that we want to choose.